We are starting recording.
Please be aware that this meeting is recorded. If you have any objection, please speak up.
So we've got very exciting speakers today. Peter from NVIDIA will start, and then Costin actually from Broadcom will continue. So Peter needs to drop at 9. So if you have any questions to him, we will take questions immediately after his presentation, but he can be present later on. And we're about to start. Peter, screen is yours.
Do you want me to share, or you have a slide?
Yes, please share.
Okay, let me find the right screen to share. Give me a second.
At the bottom of your screen, there should be a share button.
Oh yeah, I see the button. I just need to be sure I share the right thing, not something confidential. That would get say screen 1. Let me try to share Chrome.
You can also share entire window if it works for you.
Can you see it? Okay, it looks like it's working. Okay, tools.
It's not in presenting mode though.
Yeah, give me a second. Is it better?
Yeah,
perfect.
Okay, now I cannot see you, but I can see the screen. Thanks for having me, guys. It's good to be back on WebEx. Unfortunately, I cannot join in person. I wish I could. Today, my focus on my presentation is to capture the effects that AI ML inference is having on networking, particularly on the scale-up networks, and attempt to capture the specific traits that define these networks and how they differ from scale-out and things you probably know well before this presentation. A quick disclaimer: it's all my opinions, all that stuff. And all information I gathered is open sources. You can always find it out, and I try to provide links where I can. Anyways, so we'll go over a few topics. We'll look at how LLM inference works and how this affects the networking requirements. Things like distributed inference, disaggregated inference, and KV caching are essential for large model inference, and they require networking involvement to work well. And then we go about specific trade-offs that we have to make in networking for inference systems. I'll try to capture the whole story in the end in one big picture if you have time. So let's rush through it a bit because I have a bunch of slides, I realized. So first of all, a quick teaser. This is from open specification from UEC. Slides that captures the structure of a modern ML AI network. You see it says XPU, which means generic processing unit, not just GPU. All-encompassing picture. The 3 important components here is the backend or scale-out fabric. You also can hear us call it east-west very often, even though east-west was used for something else before. On the right, front-end fabric, or north-south, as we call it sometimes, but typically accesses storage. And in the middle, you see the scale-up network that connects the XPUs or GPUs or compute units together. And typically that's something like memory fabric, but it's not very well known in the IETF in general because it was always been somewhat proprietary to many vendors. But anyways, this will be focus of our presentation once we go through the principles of inference and how it relates to networking. So a quick bootstrap. I apologize, maybe too quick for some, but LLM or a large language model is a variation of a deep neural network. Things that began becoming popular probably about 15 to 20 years ago, when folks realized they can build a many-layer neural network with lots of weights and matrices and get better results in approximating the function prediction. LLMs specifically focus on modeling the text continuation. So you give it a sentence or a text, and it attempts to predict the continuation. To people's utter surprise, things start being very accurate at some point, despite the beginning was very modest. If you remember, like language modeling in the 90s or 80s was pretty weak, but suddenly when we moved to things like word-to-vector embeddings and then transformers from RNNs, people realized they can train much faster and build much bigger networks and approximate text much better. And of course, we all remember the events of the last 3-4 years, the revolution of LLMs, and all the impact it made on the area of coding, data processing, and chatbots. What's important about LLMs is that it attempts to do prediction by using two things. The data stored inside the weights in this gigantic collection of numbers, but model is being trained to produce. And second one, the context, the information which comes from a user like you sending a request to chatbot, but context often includes our data, a system prompt, or additional information which is often appended to form a bigger context. So often when you submit like a short request to a model, it concatenates this with all your past history, past context, so it processes much more than just your request. But that combined input produces the continuation or answer to your question or query. So this picture captures a high-level structure of language model that has n similar layers. Typically, all these networks, despite some differences, have the same simple structure, logically simple. Actually, in practice, it's much more complicated. It has n layers. For example, Llama 17 has 80 layers. I think Llama 405B had 128 layers and so on. DeepSeek has, say, 60 layers, 61 layer, apologies. And every layer has, at the very coarse granularity, two components, attention and MLP. Attention being, sorry, Peter, I see your hand, but I probably need to take questions afterwards because I have a lot of material to cover. So I want to go through while I have time. Anyhow, the essential part here is that there is recurrent or repeating layers, and your input on the left is a batch of queries. Batch because typically in production, when the model is hosted on GPUs, you collect the requests coming from multiple users or applications, assemble a batch. Here, vertical dimension in this batch is the sequences, horizontal is sequence length. Typically, they're being padded to form same length for every dimension. And ISL is often used as input sequence length or number of tokens that you receive in every sequence. So these requests then arrive into the model, get converted into embeddings or vectors. Embedding is the same as a vector, which is a collection of float digits, but represent this token in an embedding space. And when you run this batch through a lot of multiplications on matrices in every layer, like attention calculates interaction of tokens, MLP does the prediction, and you repeat the same thing on the sequence of tokens sequentially. The important part here is that things are sequential. You have to go for every layer in an order. There are different tricks to optimize this, like early exits or prediction across multiple tokens, but we won't go there. But the important part is that after you do one pass, you have to loop back around many times to keep predicting the sequence. And as every time you emit a new token, you prepend it to be a batch and continue the inference like all over again. This may sound quite sequential, right? You can ask, where is the parallelism here? So parallelism happens at the matrix level when you multiply these vectors that represent the words or tokens by the weights. You have a lot of multiplications. Like MLPs are pretty big matrices, like say 8,000 by 25,000 numbers. They get multiplied many times, so it gets pretty heavy computationally. I want to recap some terminology you often hear when people discuss LLMs or inference. So we just already covered batch, sequence, and token. But to recap, a sequence is it's a collection of tokens, ordered collection of tokens. It's ordered from a user or application. Batch is what you aggregate to feed into the model. Then activation is often what people call conversion of these tokens into the numbers, right? That's what you feed into the network, which you pass across the layers. So that flows through the layers. Activation means they feed into the matrices per multiplication. And the size of each activation is hidden dimension of a model. like a vector, but represents how big is your multidimensional space that models the language vocabulary. And typically you see something like 8,000 or 7,000 numbers that represent one token. So people often forget this, but this was one of the biggest breakthroughs, being able to model tokens or words, well, not exactly the same thing, but similar as vectors in a vector space, and then find out that interaction between tokens can be modeled as vector operations like scalar multiplications and proximity in vector space. That was pretty big, by the way. Like Google did this work a lot early on, like in a project called Word to Vectors. And importantly, it's often forgotten, but kind of omitted from discussions, but at the beginning of a model and at its end, this green blocks I call them green, embedding and de-embedding, or embedding an output layer, which take the vocabulary, your token collection, and convert them into vectors, and output does the reverse, because you need to translate eventually your numbers or vectors into words. And the bizarre part is that it makes sense. If you run these tokens, you actually get words that make sense based on the predictions. So remember, between the layers, you pass activations. Inside the layers, you multiply matrix weights by activation vectors. So this is how you run the calculations. Overall, it's a lot of math, a lot of flops per second. And frankly, what made this thing successful is the abundance of computing power. I mean, no thanks to NVIDIA and other companies who were investing a lot into building these parallel processors, which made deep learning so successful. So once again, we'll repeat the important part about inference. Inference is autoregressive. Even though initially at the big batch, and we process this batch to calculate the activation collection of activations, we then repeatedly sample token by token. So once we run this first initial batch, when we have to produce one token at a time and run it through the model. So after this first phase, your inference works quite, I would say, inefficiently, because you have to wait for next token to predict another one. So this diagram below shows you this loop, right? You have once upon A, you get one token, you feed it back to the same model with a longer sequence, and you continue on and on. At some point, you, of course, you truncate the sequence because you don't fit the attention window, but you have to continue the sequence loop for almost forever until you get like an end of sequence token from model, or until you reach some limit on the tokens you can produce. But what eventually defines your experience of this model is the generation time, right? You send your request, you wait for this text to complete, right? Be it coding output or be it your chatbot interaction. What's also important is that majority of this input, the initial batch, it remains the same, right? You just prepare new tokens, but this massive body of initial text, if it was massive, right, it doesn't change. So this is important because, as we'll see, we can cache this data, keep it in memory, and that's a pretty big thing in the inference. It's called KV caching. So right, actually KV caching, next thing. So KV is a key in value. This terminology is used to describe how LLMs compute attention, which is a fancy word to describe how tokens influence each other in sequence. So attention gives you scores that tell you how much my token depends or interacts with the others. And that was the foundation of success of transformers, the attention mechanism, because it allows you to model interactions in the tokens in the sequence very accurately. But when you calculate attention, for every word, you project or compute three vectors: key, query, and value. They called so because they resemble how key, query, value interact in KV stores, key value stores. They're actually very similar logically in implementation. But the important part is that key and value vectors, they remain the same during the inference, right? Only query gets changed and applied to produce the attention scores. And so to avoid the computations, always projections, extra projections, you can store them in memory of a GPU. So you trade compute for memory. And that's a pretty big thing because it converts inference from compute-bound problem to, I would say, both compute and memory-bound problem. Because now we have to materialize this KV cache, and the size is proportional to the number of input of the tokens, and keep it during the inference the whole time. That's a big thing because you'll see this is essential in every inference operation. So this is from excellent, actually, I think excellent Google's TPU scaling book. This diagram on the left, pay not much attention. It's a fancy diagram, describes the transformer layer. See, it has attention MLT in a great details. It captures all the matrices, but we won't go there. But if you're curious, read this book. It has a bit of some maybe requirements on this on basic math, but explains well how transformers work, and if you spend some time with pen and paper, you get a pretty good understanding. But the important part is that I want to capture here is the small model. Oh, well, not small, relatively medium-sized model, which was popular last year, Llama 3B, 70B. I want to give you numbers to get the impression how big are these layers in memory. The attention layer in Llama 370B is about 150 million elements. I would say elements, it could be numbers, but it depends on precision. It could be like half size, half byte, for example, FP4, or full byte or 2 bytes, FP16. So the encoding, the precision, it's a pretty big thing in the computations. The smaller, of course, the precision, the less accurate and the higher level of errors you get, but the higher the computation speed, of course, throughput, and the better memory properties. But what's important here is that MLP size is 700 million elements. So you can see MLP, the weights dominate the attention storage. Like attention matrices are much smaller in typical. That remains the same in every transformer. And then there is embedding layers, but they are only stored once per model typically. So even though they're big, they're not that significant. If you add up all these things together by 80 layers, you get 70 million parameters. So number 70B roughly gives you an idea of how much memory you need to store the model weights. And let's say if it's FP8 precision, you have to have 70 gigabytes to store the model. Okay, and then KV cache is 160 kilobyte tokens, elements per token. So every word you type cached requires 160K elements, which doesn't sound maybe too big at first. For comparison, other models have smaller requirements on KV cache, like DeepSeek is about 16 kilobytes per token because they use some very smart clear optimization tricks. But that also tells you is when you have to do the inference, you have to think about memory for KV cache. And just give you an idea of how big of a sequences for different applications. Let's say made by me. It's not like any industry reference, but here we have input sequence and output sequence. So the first row is chat. Your input is small, like say 128 tokens. That's my number. It's rounded up power of 2. It's also short output, right? Even though input is small, there's also hidden prompts behind the scenes, so don't get fooled by it. But what's important is look at the other categories. So something like deep research is like agentic, right? You give a request to the agent, a small request, describe your problem, like, okay, find me or make me the slides for IETF presentation. Well, I didn't do this, by the way. I didn't ask agent to do it for me. Did myself the old-fashioned way over a weekend. But the output is large. It has to give you a lot of text eventually, go through model. Coding, on the other hand, is very interesting and I think very popular application, which became very successful this year with the advent of the advanced reasoning models, requires long context because it have to index the whole database, sorry, your whole coding base, let's say be it small or large. Mine is really small. I guess people have big databases, but it means you have a very large context, like 1 million tokens maybe sometimes, in extreme case, like Gemini supports that, for example. And that defines how much you have to store in memory as well to do the inference. And the output is pretty small. If you tap completion, you're like, well, you know, like it's like quick completion. But if you ask your agent to write code for you, like I always do, it could be a bit longer, say 1, 2, 4 kilobytes of text to give you a few files of output. And the last one is summarization. It takes big bulk of code or data or whatever you give it and gives you a summary of it. You know, it's shocking how good things are, how these models are at summarization. Because I remember using summarizers like 20 years ago. It was horrible, right? It would just give some mostly garbage, right? But I think summarization and coding are two very impressive applications that work well, right? But usually don't make up stuff, right? Because summarization takes existing data and coding has to be tested and validated. So unlike chatbots, it won't lead you astray, you know, in some to strange debris. But the upshot is that you have to have a lot of GPU memory to store KV caches. And as we'll see, this leads often to the need to have more GPUs to do the inference. Like in the olden days, like people would say, well, can have one GPU, one video card to do the inference, right? This was the situation when I just started working on these things, like in 2019. Like one video card, like T4 GPU would be enough. But now think about this. Blackwell HBM3 memory size is 120 gigabytes. So you can, okay, I can fit my Llama 3 70 gigabytes easily there, right? One model. But then you have to have 160K per token for KV cache. And here you can say, well, maximum can fit about 700K tokens, which is a lot, right, in GPU memory. That's pretty good. But Llama 70B is a small model, right? If you take stuff like 4 or 5B, it's like 4 times larger, well, not 4, almost 5 times larger, right? It won't fit in one chip memory. So you already need more GPUs simply to split the model and pipeline computations across multiple GPUs to be able to fit and do calculations. So KV caching was the first thing that led to, in my opinion, right, to the need to have more GPUs and create the need to pipe the data or use the network between those GPUs, right? The second thing was distributed inference. Because, unfortunately, one GPU isn't enough to host or run computation of single model. The typical reason people have to split, as we'll see, is parallelism. But first of all, as I said, model size was one of the pressing factors, and KV caches, right, to split model across GPUs. Second one was to parallelize the execution, right? You saw that the model is a stack of layers. So like, where is parallelism here? Well, for once, you can always have a pipeline, right? You can always put layers on different GPUs and run the sequence across them. So you can have a higher throughput because you can load the good old pipeline or conveyor, like since semi-crazy day, to have higher parallelism. Also, you can run computations in parallel, as we'll see, across multiple GPUs. There are a few ways to do that. But very important thing that you get by splitting the model across many GPUs is memory bandwidth, right? As we'll see, decoding phase of inference requires you to load model weights very often per one token, which is like one vector, like 8 kilobytes. But they have to load very big matrices from HBM. So their memory becomes a bottleneck. And if you split these matrices across more GPUs, when you load them, your memory bandwidth becomes, higher, right? Logically, because you have on the normalized higher memory bandwidth. So splitting gives you these three things, right? More memory, high memory bandwidth, and more parallelism. With one small caveat, right? Well, now you have all these things together, you have to communicate across the GPUs. It's not a bursting parallel, so you have to communicate. And as we'll see, there are two parallelism types, but often arise in these communications. Parallelism number one is when you split the input batch with request across multiple systems, multiple model replicas, which is the easiest one. It's pretty natural way just to scale out your system by having distribute the sequence across more model replicas. Keep in mind, it's not just GPUs, it's replicas. Every subsystem has full model replica, gets some batch and runs inference. Now, model parallel in opposition splits something else, not the batch, but it splits either model weights, like these matrices, or it also can split the sequences across the length. Like take my sequence, my request, chunk it in multiple subsequences and use them in parallel. Okay, so this is a very lame attempt to capture the three common types of parallelism, model parallelism, that you see in the inference. It's very well captured in online. You can read a lot of stuff about it, but the essence is that the tensor parallel, tensor here stands for matrix, right? It beats me why people use the word tensor, but it's stuck there. If you study physics, you know tensor is something else or mathematics something else, but whatever, no big deal. In tensor parallelism, you split the matrices. Typically in the MLP layer, you split one matrix vertically, another horizontally, and now you have shards, not full matrices across the GPUs, right? You now have better memory utilization. And when you multiply locally, and then you have to do reduction. Reduction means summarize the results across all the GPUs into one output vector. So it's called overuse operator. typically. And that works really well in the MLP layer. It also works in the attention layer if you split it across the circle attention heads, but it's same principle. You split matrices, you multiply the chunks or sub-chunks, and you put them together over network. So here, all reduced traffic volume is proportional to the output matrix size, the output activation. So it's directly proportional to the batch size here, because you multiply batch, you get activations, multiply gain, and so on and so on. The extra parallel thing is specifically applied to LLMs, but have mixture of experts. And I mean, it sounds a bit fancy. Unfortunately, the words are very fancy, but mixture of experts means you have more of these matrices that represent different categories of specialization of inference. And when you do the inference, you route your activation tokens only to some of them, right? So the gate matrix or gate function is used to pick up one of the experts for input batch. As you do this dispatch and combine pattern, you distribute some tokens to some GPUs. It could be imbalanced, but in the end, you get an all-to-all traffic pattern, combined dispatch that fans out and fans in the tokens. So once again, your traffic is proportional to the activation size and batch size. You have to shuffle them across the network. You can see, no biggie, like seems like these activations are okay. And when you do the decoding, you only have to route one token per sequence, right? So it seems like it's small, but you can have a big batch and you have to route a lot then. And then if you have small batch, you have to be very fast and save these tokens, because as you fly in the air, you wait for the tokens to proceed forward, right? You can do some tricks of overlapping, but not like universal. And last one is simplest, is a pipeline parallelism. People usually like it because it's easy to understand. You pass the activation across the GPUs in a sequence. It's very nice logically, but it has like one problem, right? Well, not problem. I'll say specific. It doesn't make you matmos faster. So you have to multiply matrices at the same rate as you do before. Like before in Tensor and Expert, you split matrices right into smaller sections and multiply them locally. So now you have less weights to process. So you get this gain from having less multiplications per GPU and less weights to load per GPU. In the pipeline, you get the pipeline effect, right? You have less memory pressure. You have multiple requests in the pipeline, but it doesn't affect your decoding rate, right? So your speed of decoding doesn't change because you have to do the same number of operations per GPU. Anyways, it's pretty efficient at big pipelining because it's the easiest one to understand. Okay, so how does this all matter, right? Now with distributed operations, expert parallelism, tensor parallelism, pipeline parallelism, they have to run on the network, which is in GPU world is typically your scale up network, the fabric that connects your GPUs. And we'll see like why soon, because it doesn't have to be, right? You can have your PCIe GPUs connected over PCIe, whereas campus could do this connectivity over PCIe, like using NTB or CXL in the future, or over Ethernet if you want, or InfiniBand, whatever you like. But there's one difference. Scale-up fabrics that we'll see, they have typically much better bandwidth and latency. And latency of moving this data is critical for inference because you are blocked by communications for every token you produce. So literally every token you spit out has to wait for all those communications to finish because it's sequential, as we remember, because it's autoregressive, it gets additive the more tokens you have. So latency is directly proportional to the propagation delay, right, between the GPUs and your batch size divided by bandwidth, right? In most cases, bandwidth is the most important thing, right? Because you have a pretty large batch if you want to be efficient in inference. But as you get into the regime where you have smaller batches, latency becomes critical, propagation delay becomes critical. Okay, so now finally got to scale up networks. I had a very long tutorial into how inference works, but I wanted to get you to these whole things about EP, expert parallelism, tensor parallelism, and pipeline parallelism to explain how they all connect to scale up fabric. So scale up is just a colloquial term for the interconnect between the compute engines, and you've known this for a while. As like people built NUMA, OCC NUMA systems, cache coherent NUMA systems for a while, since the 90s, right? It just wasn't as fancy back then because nobody had AI. More modern things you can remember with hybrid transport, Infinity Fabric, QPI, UPI between CPUs. These all implementations that allow you to maintain cache coherent memory access across with GPUs or CPUs. So GPU to GPU thing evolved on its own. I don't think it was not. It was kind of inspired by close connectivity, but historically it was driven by the need to have high bandwidth in the connect between two GPUs. Like in the Pascal generation, I think we want to have like maximum, I forgot how many, at least two GPUs connected directly to do data memory exchange between memories. And it wasn't standard, of course. Back when NVIDIA was like, well, we had to do something quickly, so we put together this, interconnect, and share memory. And unlike cache coherent interconnect, the initial NVLink had some coherency properties, but it was primarily a bandit protocol. It was just be able to move data between the two GPUs. So you didn't have to invent very complex logic for managing cache coherency across all these GPUs, right? There are ways to ensure consistency, right? But coherency wasn't a big problem to maintain, mostly because you don't have these complicated access patterns across the GPUs working together on ML problem. Even though back when it was initially still driven by the video graphics requirements. If you remember, it was this video card connection link, which was a precursor to NVLink. And you can say, well, how come we didn't use PCIe, right? And you know, a challenge PCIe in general, it's the industry standard, so it kind of evolves slowly. Like even today, Gen 6 lane speed is 64 gigabit per second. And that's compared to, say, something like Ethernet, which is 200 per second already, right? So trying to build a high-speed thing on a PCIe was not very efficient at that point. Plus, PCIe has a lot of, I would say, legacy specific to PCIe, right? Which is not really required in these interconnects. So being proprietary was pretty common in these fabrics. So the diagonal variety is unique, right? I think like it's published on the NVIDIA blog. It's a snapshot. I think it's a Volta switch. It shows you the die picture, right? NVLink ports, right? SerDes and logic, and then the crossbar in the middle. But initially, as I mentioned, NVLink was a point-to-point connect. Then, of course, folks realized you can do switching very quickly on memory transactions. And so NVSwitch began, right, as a project. And effectively what NVLink does, it extends memory subsystem. You have a crossbar in GPU. Well, there's a lot of crossbars there to do memory access. It just takes memory transactions, perhaps does translation after some generations. It was not even like translations initially, and sends them remotely to the other GPU. So you have mapping tables in each GPU which say, for this address range, you go to that port and it goes out somewhere else. And of course, the initial semantic was load store. You access remote, load, or you put the data remotely, and these separations were synchronous. You can see instructions like LDG, STG in a streaming assembly documented online that have support for local and remote memory. And typically you can load, initially you could only load data into registers, right, from remote memory. And then there was support for shared memory and like non-temporal caching and so on. Over time, GPUs were adding more functionality to do memory access, like things like TMA, Tensor Memory Accelerator, which supported async data movements. This first became an Ampere. Back when it wasn't called TMA yet, but allowed you to do asynchronous copies as you can proceed in computation as you do loads, or copy engines that allow you to do the more like RDMA style transfers. So anyways, all these things evolved on their own, no standards, right? Just because it's GPU to GPU. And that was perhaps the key to success to this technology, because you have much less obstacles to innovation. And switches also evolved. Like switch on the right became bigger and bigger. Eventually started to support fancy stuff like multicasting and computational offload, like reductions in the fabric. Like thing like all like here, you see all reduce could be done in InfiniBand using specific implementation of computation offload. And this which could be done as well using a bit different trick called like pool reductions. But this was a big thing because it allows you to save a lot of processing on the GPU cores and instead do them in the network, right? Because it was a bit closer to the data. To give you an idea what scale-up fabric looks like, if you haven't seen it before, this shows 3 generations of GPUs, Ampere, Hopper, Blackwell, and the lane speed. So lane speed here would be SerDes pair speed, right? It's for like bidirectional simplex SerDes. So you can see it looks very similar to classical Ethernet SerDes evolution, even by different SerDes, not Ethernet. 50, 100, 200 gigabit per second per lane. And then GPU bandwidth, unidirectional. Here it's in gigabytes per second. It's not gigabits. Also doubled, not doubled. From Ampere to Hopper was 1.5. From Hopper to Blackwell, doubled, right, to 900 gigabyte per second. But what's most curious is that also the domain size NVLink grew very quickly. Ampere was maximum 8 GPUs on one board, a PCB rich for the switches and the GPUs. Hopper was the same, but Blackwell is now, it's a whole rack. It's a way bigger system, which to people in IETF probably reminds a lot of routing chassis. You have like backplane, with compute blades, networking blades connected together. It was a huge step up function, right, from Hopper to Blackwell, networking wise. And 70 GPUs was a number chosen to have some resiliency. We have more GPUs in one domain to have like failover capabilities. And I want to quickly comment that NVSwitch at least supports scaling. You can stack the switches. This is from our blog announcement on H100. I won't say it was utterly popular because people, I think, still try to figure out how to operate something like 8 GPU or 64 GPU system. But in principle, you can build multi-layer networks out of the switches. And right, it's even done before, right, in the lab experimentally. But I think focus right now is on a single hop scale-up networks, right? People want to connect GPUs together in one rack on one board and make this work reliably before move to bigger systems. And also bigger system at this bandwidth is, power hungry. If you do it always optical, right, it gets power intensive, right? And people are a bit cautious about power and of course costs as well of the optics to connect these things together. But typically, the biggest difference between scale up and scale out is, first of all, bandwidth, right? If you look at NVLink, the bandwidth is 9x more time roughly than scale out. So if you do this optically, good luck. It's going to be very power hungry. It probably will work, but you pay a power price. The most important part of scale-up fabrics with transport is that in the silicon, right? It's lots of logic is done, transactions, packetization and depacketization tracking in the silicon. So area is a big deal. We have to have SRAM buffers to do retries and other things. And this takes away from compute die, right? So remember, like every time you put more IO, you have to take away from area on a package or interposer or on a die, and this leaves less room for compute. So you do have various tricks like stacking or bigger interposers and so on. And all moves into the costs very quickly and power. Costs mostly, right? You have bigger interposer. Third thing is that scale-up fabrics, initially at least now, like with more extensions, give you direct memory access, like pointer-based access. So your C code just have like, well, not C, NVCC code, pointer array access to remote memory, which is very convenient, right? If you write code, it can be done. Also, warp scheduler on GPU can detect when you stall and deschedule your warp. So it has a lot of opportunity to do efficient scheduling overlapping, right? Unlike if you do like RDMA ops, it's much harder, right? You have to schedule, prepare a buffer, have a connection, give it a kick, get the completion event and so on. So it's much more involved. And then, as I mentioned many times, because of this bandwidth, you have to pay attention to power efficiency. So very often you see these fabrics done in a copper, right? In a close proximity, not because people like these gigantic racks. I mean, maybe we do like big racks, but anyways, it's just because you have to be power efficient, right? And that's pretty hard. Building these dense racks. So imagine you have like, I don't know, what is it, like 18 per GPU, right? So 32, 36 pairs per GPU. This quickly becomes very massive number of wires to put in your rack. And finally, even though it's not unique to NVLink, it was done before in InfiniBand and Cray and others. You can do computational load in the network for scale up, right? It's very common because at this rate, you want to save some bandwidth or save some computation by doing this in the switch, not in the compute engine. So once again, what you get from these fabrics is bandwidth and latency. Latency is low, bandwidth is high, way better than, of course, you'd get on, say, Ethernet, still because of the nature, right? It's very simple connectivity model. And so how do you program this? A very quick tutorial. You don't have to be digging nickel. There's a good paper people published detailing how nickel works on the fabrics. But you have two GPUs. Every GPU has a bunch of SMs, 3 multiprocessors. And this, in a very basic form, act as data movers, right? They push data through the from send buffer to receive buffer using intermediate FIFO queue to signal completions, right, and maintain memory ring. But eventually, in its essence, the communications follow latency straightforward. You copy data, so you have to consume cores to copy data using stores. The remote side does polling, detects the completion, and moves on to the next node. But logically, it's very straightforward because there isn't that much math or logic to do here. Of course, your CPU has to push these kernels, like Nickel does that, on your GPU, but do this communications for you. So importantly, you take away from your compute when you run these data movers, right, on the GPU. What are various ways to optimize it, but we won't go there, right? There's TMA, there's copy engines, and 3 other things. All right. So one real hard thing is always latency, right? Everywhere in networking. Same as in scale up. If you have to optimize your latency, well, you can, of course, add more bandwidth, but at some point with smaller batches, it doesn't help. Your propagation latency is dominated by over time have to cross the wires, the RX, TX, the interconnects between the dies, like UCIe or something like this, because we all have protocols that have the communication overheads. And you often see, today there are attempts to build open standards for scale-up fabrics. We all quote latency, right, as a primary thing. Well, the thing is that latency is end-to-end thing. So there's a lot that comes from your compute engines, right? Time it takes you to push data through the crossbars in the memory subsystem, cross the transmit-receive side. Like in this picture, we have 2 hops just across the network, right? Hops, like wires here, TXRX, which you have to put the data, FEC encode it, FEC decode it, then you do core switching, repeat the same thing at least once our time to go to the other guy, our GPU or XPU, whatever you call it, do again processing and push to HBM. So this may take easily like one way, let's say microsecond, for example, for scale, even more, right? Depends on your system because you may have load in the core switch. If you have all traffic for EP, except parallelism, you now have contention, right? And you push back to your senders and queues build up, and now you have a contribution from dynamic latency. So here I listed, we have static propagation delays, dynamic queuing effects, queuing and FEC effects. Like FEC, if you have an error, right, you have the correction path, so it adds latency. And then comms type, well, error propagation is now a whole story, right? But anyways, comms type could be reads, which means you have round trip, or writes, which is better latency because you do one-way shot, but it means your receiver has to detect your write, right? Somehow you have to signal that you have finished your writing, and the receiver usually polls to do low latency communications. So I don't have time to talk about error propagation or error handling. It's a big deal in these things, right? Because you have very simple components at your endpoints. If you lose a packet, you don't have much, freedom to handle it. Your application is very simple kernel running on the GPU. So implementing reliability in scale-up fabrics is non-trivial. So very often the reliability of underlying layer like copper or PCBs is extremely important, right? As always is. So achieving very low bear rates is essential to make these things efficient, because you can always add logic in overcorrection and recovery, but if your underlying layer is noisy, right, you just spend time retrying all the time. It doesn't help much. It's very tricky. Very quickly, I spoke about NVLink obviously because I work for NVIDIA, but there are open standards or attempts to be open standards to create scale-up fabrics. UALink is one, right? UAL. Broadcom SUE. The name is a bit unfortunate, I think SU, but that's fine. They're both Ethernet-based, obviously, right? Because what else can be used these days? Not fiber channel, I assume, right? And they both, good thing, have all the documentation now, right? Starting this year. So it's good if you want to go read about them, how they work. It's very interesting. The biggest caveat of all these things is that despite being open, it's a hardware thing. You need the compute engine to pair the scale-out fabric to something, right? And so it can't be just like, oh, look, TCP specification, implement this in software. Of course, you can do this in emulation or simulation, but to build this thing, you have to build a compute engine, like IO chiplet, and connect this chiplet to your compute engine and so on. So that's a bit trickier. It moves into this openness of silicon ecosystem, which is much trickier thing than openness of software ecosystem. And so, well, why is the big deal? Scale-up is a big deal for inference. We kind of covered this already, bandwidth and latency. So here's again the diagram of inference, going token by token, right? This is from, I think, Hugging Face. Very nice diagram. It shows you, as you remember, we have this initial first shot, big batch phase. It's called pre-fill or context or prompt processing stage. It's mostly compute bound. You have to calculate KV caches for all these tokens. And then you have this routine, mundane process go for token by token. So always TPOT, time per output token, is bound by latency of your interconnect, right? Because you have to perform these multiplications across the multiple GPUs, right? Or push the data. And latency, as we described, is based on bandwidth and your propagation latency. And total time to finish this query is your time to do the pre-fill, process all tokens in one shot, and then do this decoding rate, token by token. And you don't know how much tokens you're going to have, right? You may have a lot of tokens, may have not much many tokens, right? But all of them are bound by your fabric latency. And so it's, of course, essential to expect that when folks implement distributed inference, they want to do it on the scale-up fabric. Oh, shoot. Okay, I only have 10 minutes left. Realistically, I wanted to cover a bunch more stuff. I'll probably skip this. This talks about the trade-offs between decoding rate and decoding throughput. It's very, very important for operators or practitioners because it shows you that if you load lots of sequences in your system, you achieve very good throughput, but your per token latency gets much worse, right? But this curve is very well known to engineers in general. It's a Pareto trade-off frontier. When you design your system, you have to pick up regime which is optimally fit to your needs in the moment, right? And the right corner here is the most interesting one because this is where you're primarily bound by the comms latency, right? Because you have small batch, all you have to do is you pretty much have exposed latency on your fabric. So here, this is where you have very fast sequence production for like one batch or one sequence, right? And this is where perhaps people think this regime is best fit to the AI agents because it's very good for chain of thought inference. It's fast generation of a chain of thought. Unfortunately, this regime is also very inefficient throughput-wise because your batch is small. So you can say, financially, it's pretty hard to justify that regime. So very often you see practitioners focusing on this left corner, tokens per GPU. So they have larger batch, they partition their models such that they maximize the throughput and not the latency. This is a wonderful diagram from Perplexity blog. If you have time, go check it out. It shows you pragmatically how you adapt, as a link below, how you design your system to achieve different regimes, right? High throughput or low latency. It shows you this, familiar text, EP, TP, DP, dimensional parallelism, and how they affect your performance in a throughput or latency. So I'll skip that, but please check out the blog. It's very interesting. It doesn't use like the latest systems. It uses Hopper 200, I think, H200, but it's very good to see in practice how these choices affect your Pareto points. Once again, this is why scale-up became a big deal for inference, not just for training. There's, of course, application in training, but inference, which has become a dominant driver of compute demand these days, depends critically on these fabrics to be performant. One thing I want to cover is also very quickly is disaggregate inference, DSAG. Remember, we just spoke about distributed inference, but also DSAG inference. Thanks, right, guys? Helps a lot. So remember, we just discussed that in inference, you have these two phases. You send the batch, you have to calculate the KV cache. It's called pre-fill or context. And when you do this compute-bound memory-bound token generation phase. And prefill is almost entirely compute bound because you have so many tokens, you're bound by the time to calculate the attention scores for all these tokens, right? And whereas the decoding is usually memory bound, memory bandwidth bound in most cases, there are other trade-offs. So it makes sense to split these two phases in different GPUs, right? In different hardware systems. So one is optimized to do higher compute throughput. Next one is optimized for latency. So this is called disaggregation. This is a wonderful picture from one of our blogs, very green and so on. So typically in most systems, it was easier, of course, to do with two phases together. You get a batch, you calculate the prefill, you get the first token, and you want to start producing the decode. But while you do prefill, usually you cannot do decode. But if you pipeline them, on the right figure, you have prefill machines and decode machines. You can now do prefill and decode in a pipeline fashion. So while prefill calculates KV caches for one batch, decode does decoding for the next batch, so for the previous batch. And it's all, like nice and synergetic with one small caveat. You now have twice more machines to manage, right? I mean, not twice more physically, but twice more logically. Usually what you do, you take same, say, GPUs, you partition them into two pools. One is prefill pool, and another is decode pool. And when you route a query, is first to prefill and to decode. But now you have to pass the KV cache between these machines. And of course, you can I use scale-up fabric for that? It comes out you can, right? You can also use east-west or scale-out fabric because here latency requirements are less critical. About depends like on your output sequence length. If your sequence is very short, you have to be very fast moving KV caches. But that's another dimension, right? Another dimension. As I mentioned, the way it works, you have two pools, same model, right? Exact same model, but it's a bit optimized differently. One is optimized to have like a high compute throughput, which is usually pipeline parallelism. Next one is optimized for decoding rate, like say tensor parallelism, X-acid parallelism, like sharding. They can be even in one rack. Like if it's a great Blackwell, you can fit these two phases in one rack on different blades. Usually there's enough space to do that. This is nice because you can use now Venable Link to use all communications, but you don't have to, right? You can always pass KV caches using like east-west network as well. But remember, what you communicate between these two phases is KV cache. Prefill calculates KV cache for the batch, you push it to decode, and decode goes in the cycle doing this token emission. And then finally, you can see, okay, what about my chat history, right? Or something, my code base. We just discussed KV cache as being always in memory, but in reality, it's always also part of your history, right, of your past conversations. So that thing you can store in a offline storage, be it SSDs locally or remote SSDs or something else, right? Because you need to, plonk and pull this cache only when you restart the conversation. So you chat history, come back to, ChatGPT, you type new question, it pulls back your context, right, from the storage. So that's very important, right? KV cache storage became very important because nobody wants to recompute the whole history you had before from scratch. It's a lot of time. But now you of course you now translate the storage for compute. And so remember, now we have active KV cache, which is what you have right now in computation, and inactive, which is storage of your old history. And you can, have pretty big volumes of storage if you have lots of users to keep a history or the code bases, offline somewhere. It's a big topic, but KV cache also connects to this cluster. So now, okay, finally the picture I promised in the beginning, we made it here. So on your left, so okay, on the top, first of all, is our east-west scale-out network. East-west is how we call it here internally for whatever reason. Let's say it's Spectrum or InfiniBand or whatever fabric you like, right, for scale-out. Connects GPUs together. The left block, let's say this is your fancy GB200 machines, big and link domains. They run your decoding part, right? They run decode piece because they have lots of parallelism, like tensor parallelism, X-acid parallelism, for example, DeepSeek. On your right, you have your prefill machines. They don't need as much of NVLink bandwidth, even though actually it doesn't hurt, but it's not as beneficial. You mostly do pipeline parallelism, but they do prefill. So when the query comes in, it hits this block first. One of the machines here, it generates KV cache, and KV cache goes to the decoding on the left side. With one small thing, if you also have a history, you can have to pull in KV cache from storage, which could be typically on your north-south network, like your front-end fabric, and it stores your history of conversations or your coding database already tokenized and KB cached for your model. So all this thing is just to say computation, right? If all GPUs are very compute heavy, it's not that heavy, to be able to do everything from scratch every time. So caching is extremely important for inference efficiency. So that's the full picture, right? Scale-up network is most critical on the left, right? For decoding, it's essential for high performance. It'll also work on the right because, if you have the same machine types, why not use them both together in one rack even? But then for KV cache transfers, you can use east-west scale-out network. Typically, the bandwidth is sufficient there, more than. On the north-south, you have storage, right? Whatever you use to store KV caches, typically somewhere on SSDs. But supposedly I made it to recap in time, skipping it only a few slides. Let's say just what's important to remember here, right? Inference became a big driver for networking or GPU demand since probably this year. Mostly because I think people start seeing real products taking adoption, like coding tools especially became a huge thing. And now it's, to make it all work, you have to have compute, right, to do the inference for users. For many times, I think many years, it's all about like training, like bigger and bigger fabrics. I'm not saying they're going away. I think training is still a critical problem, but now product drive the volume for inference. And inference is a bunch of distributed multiplications. So you have all these fancy parsing types, but have to communicate over scale-up fabric, right? KV caching is essential part of LLM inference, which creates you both memory pressure to store KV caches and also generates traffic to move KV caches between the sub pools. A very important thing, which I didn't have time to cover, is this whole Pareto curve, how to pick a optimal point and how this is influenced by the network, right? Because network is very critical on the right side, or as you go farther to the right, you get more and more network bound in these curves. And as I mentioned, wherever possible, it's profitable or beneficial to run distributed inference over scale-up fabrics because of bandwidth latency and so on. But for KV caches, bandwidth isn't as critical. Although there are cases when you have to get answer very, very fast, say you have a very short sequence, very have to be much faster moving your KV cache. But in most cases, you have long sequences emitted out, so your time budget overall for KV cache transfer is much more relaxed. And hence, for KV cache, and you can use your traditional, so to speak, Rocky or InfiniBand or whatever fabric you choose. Well, but if you have much choices these days besides Rocky and InfiniBand. But that's it. Thank you so much. I apologize. I had to go straight through without questions. I hope people could hear me. Thank you for listening. I would love to go more details if we have more time, but unfortunately not today. I have to run to real life meetings, which still happen here. Thank you so much, Jeff, for inviting me.
So much, and we hope to see you next AITF.
I'll try to, yeah. I'll try to one day make it in person. I promise. I miss it a lot.
Have a good
Thank
day.
you,
Thanks.
and I wish I could hear the next presenter. Thanks, guys. Bye. Have a great IETF. Thank you.
So if you have any questions to Peter, I know it's a lot of technical details and probably the best presentation on inference I've ever seen done in 1 hour. Send us the question, we'll forward them to Peter and kind of figure out how to come back to you. And now we are moving to next presentation. And do you need to do anything?
Konstantin, maybe you can share the slides from your own laptop.
Yeah, you can share the slides and drive them. Probably more convenient.
Yeah, that's probably easier.
Yeah, can you see my slides?
Yes, yeah, we can see our slides. Thank you. You can
Okay, great.
start.
Thank you.
Yeah, indeed, fascinating talk by Peter. I really enjoyed that. Thanks for the invite, Jeff and Inchan. Honored to be here. Okay, so the focus of this talk is on the scale-out network. So it's a nice complement to what Peter has presented earlier. And this one is a bit more networking heavy. I will try to motivate a little bit why the networking has to do what it has to do, but most of the focus is really on the networking side. So this basically just says the obvious, right? So we used to have these CPU cloud networks that people understood, many tiers, typically just flow, and it used to be either TCP/IP and some RoCE/RDMA for storage, and really the driver for the implementation for the transport was in kernel, and this was TCP/IP and variation thereof. And the scales were pretty large, 100,000 machines are common, but job scales are not necessarily the full data center, right? So maybe 10K or something like that is something common, but not much larger. At the same time, with this kernel transport, typically any single flow did not take a lot of bandwidth. So maybe you have like a few gigabits or tens of gigabits per flow, but not more. Whereas the NIC speeds were like maybe 10 times higher than the flow speeds on average. And because of this, load balancing via equal cost multipath worked really, really well. So when people started building separate networks just for GPUs, and they started building this mostly for training, but now, once they're built, these things will get used also for inference. So typically the networks are larger because you're trying to interconnect more endpoints. Like, we've heard news from, OpenAI and Microsoft of saying, we want to have like 1 million nodes in this and stuff like that. And the difficulty here is that you want to connect them with really high speed, right? So now the bottleneck is not necessarily the host transport, like in the case of kernel TCP, but rather the actual NIC and the network. So these networks have much higher cross-section bandwidth compared to the cloud networks. And because of this, they also, there's a lot of optimizations, to sort of ensure that they are cost-effective to build. You don't want many tiers because at every single tier you have to have optics. Obviously, the first tier you can avoid optics, but everything else you pay a lot for the optics, and then it becomes really unmanageable. So really, there's like a quiet sort of revolution happening here, where people are building, these new networks, and really transports are being developed as we speak. And this is the focus of my talk. And again, I'm going to use the same picture from the IET. Basically, the focus of this discussion is this yellow network here. So how do you interconnect the GPUs via a data center-wide network? I will add that recently, because of power density, people have been talking about distributed sort of training and having transports that go across data centers in different geographical areas. This does not cover that. This is not intended for that. So this is basically intended for a network where the RTT is, say, in the order of 10 or 20 microseconds, and you really want to interconnect GPUs that are in the same campus, right? So within fairly close proximity of each other. And I'm not going to cover the scale-up network that Peter covered. Okay, so a lot of my talk will be just the nitty-gritty details of what a transport looks like for this type of networks and why we need it. But I will say that a lot of this work that I've been doing in this space. But by the way, I have two hats. I'm part of Broadcom. I came into Broadcom as part of a startup acquisition, and also I'm a professor in Bucharest, and my work has been on data center networking. So as soon as we joined Broadcom around 2022, there was this consortium called the Ultra Ethernet Consortium, with the stated goal of creating a transport over Ethernet for scale-out networks. That was the stated goal. And this is the sort of the protocol layering and the architecture of what came out of that. So the first specification came out literally just a month ago. And it's been like a 30-month sprint of multiple companies, including hyperscalers, vendors, and so forth, to define basically all of this from scratch. And having been to the IETF and having contributed the multipath TCP to the IETF a long time ago, I know that this is shocking that people can just go and do a full new transport sort of outside the IETF. I'm not going to go into that. It's really not it was not my decision. I was just one technical person doing this. Okay, so let me slowly take you through what the UET is and sort of how it's different from the existing RoCE/InfiniBand stuff. I mean, I'm going to go through this fairly quickly. And then we can focus on sort of the details of congestion management and packet delivery, which is really where my work has been. Okay, so the upper layer APIs that were adopted by UET were the libfabric APIs. The reason for this is because we wanted a sort of a connectionless service that is not built around the concept of a pairwise connection between two endpoints, like a QP, and this is because that thing is known not to scale. So the UET, the main targets for it are not only AI networks, but also HPC. In the context of HPC in particular, scalability is a big thing, and having to sort of have long-lasting QPs to everyone you talk is sort of a well-known big limitation, and that's why the libfabric APIs have been adopted. That said, there is work to provide a verb mappings over UET, and that work is ongoing. Okay. So the semantics layer is basically what gives you the remote memory access semantics for UET, and it has the operations you might assume exist in such a protocol, such as send and receive, write, read, and atomics, and all of these are obviously zero copy. The key difference from sort of Rocky / InfiniBand is that since the QP is no longer the main thing when you're talking to someone, you don't have an associated receive queue necessarily, and the receive key is really shared across the node. And this helps scalability, but introduces some other issues. The addressing itself is scalable, and there's some extensions that I'm not going to go over because they are just too detailed. Like if we have time at the end, maybe I cover them, but I'm just going to skip them. Okay. So packet delivery-wise, to have scalability, basically, we have host-to-host connections, transport connections, and on top of these transport connections, you can carry, as many sort of semantic messages as you want. And these connections are set up in 0 RTT, and they take 1 RTT to close. And there's 4 modes in which the UET works. The most interesting one is reliable unordered. The other ones are either for legacy reasons, like the reliable order, which is basically go back in, and the idempotent one is sort of HPC sort of specific. So the focus of this talk is really this reliable unordered delivery service, which means basically you'll have to like sort of spread your traffic across many paths in the network, and the receiver has to deal with out of order packet arrival. And of course, you need, to be able to place data directly into the memory. You cannot buffer it on the NIC. And then you have to be able to deal with selective acknowledgements and so forth, and retransmission. And congestion management, we're going to talk about this a lot, so I'm not going to go into the details here. And also there's a security layer that again is sort of pretty standard. It's very similar to PSP at Google. But it's an optional thing. Okay, and sort of in terms of high-level overview, this is the header stack. So the protocol can either work over UDP or directly over IP. So it supports both modes. The security header is optional, so you can enable that if you want security. Otherwise, you just don't have it here. Then you have a packet delivery layer header, which is this one, the PDS request, and then the semantic layer, payload, an optional CRC, and finally the frame check sequence. So I don't think this is anything particularly controversial, so I'll just skip next. So let's go to some details. Like why was there a need in the community, in the industry, to build such a protocol, right? This is a sort of a multipath protocol with out-of-order placement and so forth. And, and actually it's not multipath as in multipath TCP. It does this thing called packet spraying, where sort of every single packet can go its separate way. So, why do you need that, and how do you build it? Finally, I'll talk a bit about, how does the congestion control work? And what is this thing called packet trimming, which is sort of a novelty in terms of switch processing of packets. Okay, so I'll sort of follow Peter's lead to try to give you some context on why people ended up saying, okay, we need a multi-path transport. And the reason for this is, well, you've got these accelerators, and what I'm drawing here is, some nodes, okay? And what I'm showing here is layers from the same model, right? So we have this. There's this paper we published last year in Hotnets where we basically said, what is OpenAI going to do with all of this infrastructure that it's building? So famously, OpenAI came up last year and said, we're going to invest 100 billion in sort of infrastructure. And we basically went out and said, okay, what can they build with this? And this is sort of a university paper, there's no proprietary information whatsoever. It's just sort of a reverse engineering of what can you do with all that money, right? And we came up with some numbers. Basically, they can buy like 1.6 million NVL, Blackwell GPUs and so forth, and they're going to have this many racks, and they need to split it into data centers and so forth. And then, if you have this, what type of model can you build? There's this scaling laws that says bigger is better. So basically, we said, what is the largest we can fit on this infrastructure? So we came up with this, round numbers like 100 trillion parameter, right? So GPT-4 is like 2 trillion, and we said, okay, if you want to go big, maybe 100 trillion is a bit crazy, but let's see what that means. Okay, so if you want to train 100 trillion parameter, basically what you're going to do is you're going to take a layer and split it. Layer 1 here is actually on 18 GPUs in this rack, and on layer 2 is on 18 GPUs in this other rack, and so forth, right? So basically, you've got 18 of the 72 GPUs holding a single copy of layer 1 and so forth. So now, when you've got your say tokens coming in, as this thing comes in, activations are computed. The stuff coming out of layer 1 are also activations, and these things have to go to layer 2, right? Now, if you compute the size of the activations, basically, you have to give all the tokens to all of these replicas for this to work. And the activations are actually, pretty large. So they're like, almost 4 gigabytes. So if you transmitted this over an 800 gig network, which is what the Blackwell has, that's like 38 milliseconds of exposed networking, meaning your training has to block waiting for this networking to finish, which is quite a lot. So you probably don't want to do that. So what you probably do is say, well, I've got 18 GPUs, and they've all sort of computed the same activations as this came out. So this data is already available on my 18 GPUs. I'm not going to send 18 copies of it across the scale-out network. What I'll do is I'll split this into 18 shards, and the first guy sends the first shard, and the second guy sends the second shard, and so forth. And then you basically send 4 gigabytes over 18, which is just 215 megabytes, and then now you're down to like 2 milliseconds, right? And then what you also have to do here is to do sort of a all gather operation where people just sort of broadcast their own Y to everybody else so that they know, right? But the scale up is so fast that you can literally mask the scale, right? So, okay, so the takeaway here is that the flows on the scale up are sort of point to point. They're fairly small, just 200 megabytes in this case. And there's more or less no locality, right? Like, it's literally, fully loading the scale out network. Okay. Now, if you try and see what happens when you do data parallelism. So data parallelism, as Peter said, basically you have multiple copies of your model in your data center. When you do training, basically you take your input data and you split it. You'll split it in as many parts as you have model replicas, and then you basically push every single part through a single replica. Now, this is all nice and good, but at the end of each training phase, you have to sort of reconcile what these models have learned. Otherwise, you'll have divergent models. If you're training different, distinct models, you want them to act the same. So basically, what you do is when you're coming back, these guys have to sort of synchronize, and this is an all reduced phase that they do. Okay. So what I'm showing here is basically the same layer as before. So I've got 18 GPUs holding the first replica of layer 1. But I'm also going to place 3 other replicas of the same layer 1 in the same rack, and then there's a lot of replicas across the data center. So now what I'm doing when I'm doing all reduce, I'll have to sort of synchronize the activations for this layer across all of my models. And the standard way of doing this is, by the way, this is quite large. So the gradients here are almost 400 gigabytes. So the standard way of doing this is this thing called ring or reduce. So basically, you talk to your neighbor that is close to you in the scale up domain, and then you cross a single time the scale out domain, and then and this is quite efficient from utilization of the scale out network. This is great, except it's really, really, really slow. Okay, so now what you want is to sort of do something smarter, which is basically saying, okay, why don't we all reduce within our rack? So now everybody has exactly the same knowledge within the rack. Now we can sort of partition this data, and we do an all reduce across the racks where you've got like 72 all reduces happening in parallel, and sort of you can imagine these are rings that go across many racks. And finally, at the end, you do this all together, and everything sort of comes together. So now, again, you've done this hierarchical operation, and I'm not showing this to you just to sort of make you to confuse you, but to show you that again, instead of having this nice all reduce where you have very little traffic going across the scale out, you actually have parallel flows going across the scale out, which look like this traffic pattern called sort of a permutation, where it's like one-to-one, fully load up the network core. So if you want to support this at full speed, you'll have to fully provision your scale out network. Okay. So there's very little locality in these things, especially when you start to take failures into account. And these flows start out simultaneously, and they fully load up the network. And if things don't go slow, then the GPUs slow down, and people are very unhappy. Okay, so this is basically the requirement on the scale out network. Okay, now let's take a step back and sort of say, okay, let's say this is the scale out network that we built, right? I've shown it here in 3 tiers, but typically people will try to have 2 tiers. Now it depends a lot on their own preferences. Okay, so now if I have this guy talking to this guy, there's a lot of possible paths. And the way this works is, you send some packets, and typically all the packets have the same 5-tuple if you're using TCP or if you're using Rocky. And the switches will literally hash the 5-tuple of the packet plus some sort of constant salt they have, and select out of the many paths they have towards one destination. They'll select a single path, right? So for instance, let's say this path is selected for this particular Rocky flow. By the way, Rocky is what people use today in data centers. And then you have this other Rocky flow going to another place, and now these guys just sort of get unlucky, and they sort of collide on this link, and then the throughput goes to half, and you're wasting a lot of capacity. And if you're looking at this, you're like, oh, I could do something adaptive and sort of move. If I see bad performance, maybe I can move. But it's actually quite tricky to get this right. And there's literally 15 years of work on how to avoid flow collisions and how to fully load up a data center network. Okay. So all right. So the state of the art is really Rocky, which is single path, and InfiniBand is basically the same, right? So what I'm simulating here, this is, by the way, these are HTSIM simulations, and this is simulating a 8K node network, which just has like 2 tiers, and the load is 100%. So everybody's sending to somebody else, and this goes through the spine layer. So if you look at the flow completion time of these pipeline flows, it's actually pretty bad. So some of them get 1 millisecond, which is the optimal. So they manage to find an idle path of the network, but these guys, they probably collide with a single other connection. That's why they take 2 milliseconds. And then there's like really, really unlucky guys, and they finish in like 9 milliseconds. So we're talking like completion time of like 9x the optimal. And this is really bad, because that means some of the GPUs finish their pipeline here, but they all have to wait for everybody to get their data, and basically they'll be idling for this amount of time, which is really, really bad. So there's 2 issues with Rocky, right? So there's flow collisions that I've shown, but there's also this thing called PFC, right? So Rocky assumes the network is lossless because the retransmission behavior is go back end. So that's really inefficient. You lose a single packet, you basically retransmit the full window, right? The receiver is not really able to sort of accept packets that are out of order, just drops them on the floor, and then you have to retransmit. So because of this, you enable PFC, but PFC comes with its own issues because, yeah, it avoids losses, but it has this sort of a car road effect where, it's like congestion you get on the highway. When like a single exit sort of blocks up, it blocks up the entire highway. It doesn't matter where you're going, you're still stuck in traffic. Okay, so if you sort of did away with PFC, what would you get, right? So this is simulating the same thing, but just using a sort of best effort lossy network. Okay, so it is better, but still you're like at 7 milliseconds compared to an optimal of 1. Okay, so it's really flow collision. So to get away with to sort of deal with flow collisions, what you really need is multipath transmission, right? So if you use 2 paths for every single connection, say multipath TCP style, then you can go to something like 3.5 microseconds. If you go to 8 paths, you go to something close to 2 milliseconds. So this is obviously getting better. And by the way, this is what people do in practice. So the collective libraries today, knowing that ROCK is particularly not very good with this, they will try to basically use multiple QPs, multiple connections towards the same destination, and do some sort of load balancing at the application layer. And they use typically a small number of paths, like 4 to 8, and it does help. Like you go from like 10 milliseconds to like 2 milliseconds, right? So it's a big improvement. Well, it turns out what you really want is to use a lot of paths. So if you use something like 128 paths, you're within 5% of optimal. And this is basically the goal. How do we build a transport that is able to use this many paths and actually works? So okay. So let's dive into a little bit into like what does Ultra Ethernet transport actually do? So this is a sort of a specific transport that's built for data centers, so it's not meant to be run in the internet. So it makes a lot of assumptions to get near optimal performance. The first assumption it makes is that the network-wide RTT and the link speed, right? So the bandwidth delay product of your network. I did mention that we're talking about networks with 10 to like 20 microseconds worth of latency, highest latency end to end. So basically, what you do is you have a CWIN. This is a window-based protocol. So you have a window that limits the total amount of traffic, and this is not allowed to grow beyond 1.5 band delay product. So it doesn't matter how good you think the network conditions are, you will never go above. You'll never inject more than 1.5 BDPs, right? And this has nice properties because it has nice stability properties. If you have like big buffers and your packet gets stuck somewhere, you just stop sending, right? This is in contrast to like rate-based approaches like Rocky, where you just keep sending if you don't hear anything because you assume all is good. Okay, so ZRTD connection setup is again a nice thing, right? So basically you just start sending towards the destination. The way the destination knows that this is the first RTT is because you have a flag, a SYN flag in the packets being set. And now, because this is a multipath transport, it means that the first window packets can arrive pretty much anywhere. So what you do is you set this flag on all the packets in the first window. And the packets in the first window, they carry the PSN, but they also carry the offset, sort of the start of the sequence number. And this allows you to sort of know how to place them and to sort of know where the starting sequence number of the connection is. Okay, and after you start sending ACKs back. As soon as the sender gets an ACK back for its first window, it stops setting the SYN flag, and then it goes into established mode. The receiver, as soon as it gets a packet that doesn't have the SYN flag, again it goes into established mode. So that's the connection setup. It's pretty obvious. And then the packets are basically sprayed split across all of the paths. So the way this is done is by, again, relying on ECMP. By the way, I didn't say this, but a big driver for UET was to sort of ensure that there is no vendor lock-in, right? So that's why, you know, there's like multiple switch vendors, multiple NIC vendors at the UET. And there was a lot of push to ensure that the transport does not require features that are specific to a single vendor, right? This is why, you know, in terms of routing, the common denominator was ECMP. So, you know, ECMP is well established, it's well supported by pretty much all available switches. The question is, how do you use it to spread traffic across all of the paths? Well, the idea is you add a number, an entropy value to every single packet. The sender does this. And the default is to just play with the source port, the UDP source port. This gets hashed by the switch, which, you know, results in a randomly chosen path to the destination, okay? So now you have an issue of how do you load balance to choose the entropy value for outgoing packets, and that is the question, right? That is something that the transport has to solve. Okay, so if you have this, then basically what this does is let's say you pick completely random entropy values. This probabilistically will lead to traffic being split across all of the paths, which is great, which is exactly what you want. Which means that you really cannot get collisions in the core of the network, right? So, you know, the traffic nicely spreads across all of the available capacity. And actually, this works really, really well. It's not going to be perfect because you still have randomness, and you can still place a bit more load on some paths compared to the others. So you may still have some hash collisions and so forth. So we'll see later that, you know, to what extent this is a problem. And the spoiler is that it really isn't. You can probably cope with it. Now, the big question is, why haven't people done this? Like, this is obvious, right? You know, there's been research on this. I think packet spraying was first proposed in 2015. And people haven't done it because it's very difficult to detect loss, right? So I've already said that we don't want PFC because PFC has header-line blocking. So if you don't have PFC, then you really need to use some sort of loss detection mechanisms, which in all of the existing transports are heuristics. So TCP uses 3 duplicate acts. There's you know, like a ton of extensions. There's like tail loss probes. So there's like literally a literature based on how do you detect reliably that the packet was lost and retransmit it quickly. But that's for single path transport. Now, when you have multipath, and by the way, all of the literature for single path transport assumes that the packets will arrive in order, right? This reordering breaks this assumption. So the standard heuristics for quickly detecting that a packet was lost really don't work for straight transport, okay? You, of course, will have a retransmit timeout, but those have to be, by definition, quite conservative. So the question is, what can you do? That's a big question. Okay, so how does reliability work? You send packets on different paths. Each packet has an ACK request bit. If this bit is set, then the receiver will basically send an ACK immediately. And by default, the senders are setting this bit for last packets in a burst. So you'd set it, for instance, if you know that the message coming from your end, you know, for the sort of right last packet, you'll set the ACK request for that to make sure you get an ACK for that. And you'll set it when you're running out of congestion window. This is the last packet you can send at this point, you'll set it again. And the reason for this is because we're trying to reduce the packet rate, right? So it's very easy to create a transport that's reliable if you have 1 packet per ACK, right? But especially if the packets are a bit smaller, then you'll have a lot of control traffic. So what you're trying to do is to reduce the number of ACK packets. So if you reduce the number of ACK packets, that means you can send a few packets and not get anything back because you know, this like delayed ACK in TCP, right? So this works, but it creates issues, right? So you have to somehow deal with these issues. Okay, so the ACKs coming from the receiver, they are very much like TCP. They have a cumulative ACK, But unlike TCP that quotes the PSNs received beyond the cumulative ACK, this thing has a bitmap that is 64 bits wide. And the bitmap starts at this reference ACK that is also quoted in the SAC packet. So basically, this bitmap will cover 64 PSNs, more or less, right? And then you basically set it to tell the sender exactly what was received and what not. And SAC generation, oh, I realize time is going quickly, so I will skip some detail. Okay, so I'll just skip the SAC generation, but basically what you're trying to do is to reply when the sender said it wanted feedback, or when you see congestion marking in the packets. Okay, so once you've done the spraying, you cannot have congestion in the core of the network, more or less, unless you have failures or single path flows. If everything is sprayed, you will not have congestion in the core. So the one remaining problem you have is this thing called incast. So you have 4 senders here shown on the left of this image, sending to the same destination on the right. Okay. Now, the UET starts at line rate if you want to minimize the flow completion time. So in most cases, there will be no contention. Applications, like collective libraries, are designed to try to avoid sending, creating incast or these large ones. So in many cases, when you're sending, you'll be sending and you'll be the only one. So you really want to go at line rate. That's why the initial window for the congestion control is basically the band delay for line, right? So you start at max window and you blast. But in this case, there's like 4 guys sending. There's a lot of data coming in. So because of spraying, there's no drops whatsoever going up. There's enough capacity. This topology is fully provisioned. But coming back down, you'll have a lot of traffic arriving for a single receiver link, and this is called ingest. So what do? If you use PFC here, it's actually pretty bad because you could even deadlock if you design your transport wrong. But even if you don't deadlock, because you back pressure into the network, you will do a lot of damage to flows that are unrelated to your incast, and these are called victim flows in the literature. Okay. So we cannot do PFC. So what can we do, right? We'll accept that there will be loss. But the thing is, the RTTs are so small that if you knew there was loss, you could in principle send a negative acknowledgement back, and the retransmission would come very, very quickly before the queue drains. So the big question is knowing what was lost in the context of reordering, and then when do you retransmit? Okay. So loss detection at the UET has a few methods, right? So the spec only says you must do retransmit timeouts per packet, and you must support packet trimming if the switch is supported, but trimming supporting the switches is optional. Okay, so these are the 2 compulsory mechanisms that you have to implement. However, you can also use this field called out of order count of the receiver. Basically, the receiver tells you how many packets it got beyond the cumulative ACK in every single packet. So you can use this to trigger a retransmission if you want, or the sender can keep state per EV and then do sort of in order loss detection. These are not mandatory, so people can implement it, right? And again, the reason there's a lot of choice here is to allow vendor differentiation, and also to say, look, in the case when you don't have trimming, because we don't want to force people to have trimming, because trimming is really not something that is fully available today in switches. So in case you don't have trimming, this thing still has to work, and it does. It just doesn't work that well. Okay. So the good thing is that trimming is supported, and there's multiple vendors supporting it. So now we can basically assume you have it. So what is trimming? Okay, so typically in switches, you have like 1 output buffer per port, and you have packets coming in, and you have some sort of drop threshold that is dictated by how much buffer you have available in the switch. Now, let's say this red guy comes in a normal deployment, in best effort, you just drop this and nobody knows about it. And that's all there is to it. With trimming, you don't drop it. You basically just cut the payload. So you basically take the packet, you chop it off at a predefined size, right? This is called the trim size. This is a network one configuration, and it's meant to be large enough so that you keep the transport headers, right? And you update the DSCP field inside this trim packet. So basically, this moves the trim packet to a different queue on the same port. And this queue is either strict priority compared to the data queue, or some sort of deficit route robin. Okay. So now what happens is that this thing goes to the receiver, and the receiver now knows that something was lost. So what the receiver does, it basically generates a negative acknowledgement, a NAC packet quoting the sequence number of that packet. And there was a lot of discussion of security implications for this. So what happens? What happens if people spoof NAC trim packets and so forth? Here is that the effect of a trim should never be more than the effect of an ECN mark or a congested one. So it basically will affect the congestion control state, and it may trigger retransmission. So it basically it has sort of the same safety properties as ECN / sender detecting a lost packet via another mechanism. Okay, so the receiver knows who sent this and knows very quickly. So basically, it will send the NAC back. I've already said that this thing starts at line rate. NACs tell the sender what was retransmitted, and the UEC has the UT has two different ways of managing congestion, and these are they follow different philosophies in doing so. So the first one is this thing called network signal congestion control. It's basically a novel sender-driven congestion control, and the novelty is that it doesn't just use latency, but it also uses ECN marks. So we have congestion control for this data center that uses ECN. This is called DCDCP. We have congestion control that uses latency, something like Swift or Timely from Google. This thing is uses a combination of latency and ECN, and because of this, it's able to actually be much more aggressive in sort of increasing and decreasing. And the nice thing about this congestion controller is that the target bottleneck queue for the controller is 0.75 of BDP. So if your RTT is 10 microseconds, this thing operates with a 7.5 microsecond standing queue, which is pretty awesome. And this is independent of the number of senders. In contrast, other alternatives such as Swift, they do work, but the buffer at the bottleneck grows with the square root of the number of senders in incast. So this actually gives you better properties. Okay, so this is a standard congestion controller. So basically, the retransmissions for this will happen when you have space in your congestion window. And the other mechanism is receiver-driven congestion control, and basically this is based on the observation that at the receiver, when there is oversubscription, you will know because you'll get some NACs, right? And because you get the header, you get some trim packets. You get the headers, and actually the data packets also tell you what the backload of each sender is. So you know what the total demand for your incoming link is. So this algorithm is designed for the case when you have a fully provisioned network and only the last hop link can be the bottleneck. And the way it works is by giving out credits. And the credits are spaced out to ensure that the incoming data packets come at line rate. So basically, if you do this, then you pace the credits out, and after the first round trip time, traffic will be coming perfectly spaced out. And actually, in steady state, this thing operates with a zero queue and close to line rate throughput, because the pacing can be done just slightly less than line rate, which means you can have like a zero queue, which is really what you want. Okay. Okay. So now we're down to load balancing, right? So how do you we have a window that dictates how much you can inject in the network. And the congestion controllers, they work either at the receiver by using this exact information of what the demand is, or at the sender by measuring average latency and looking at ECM marks and updating this total congestion window. Okay. So you can, how do you choose the value, the entropy value for each packet? So how do you choose the indirect path for each packet? So the simplest thing is this thing called oblivious. You just pick a random EV, and this works really well if capacity is uniform. So what I'm showing here is a permutation traffic matrix where the flows are just 2 megabytes, but this is a 100 gig simulated network. And the optimal flow completion time in this case is around, I think, 180 microseconds. So what you see here is because of this slight imbalance and hash collisions and so forth, you do get something like 250 microseconds, which is what, 25%, 30% worse than sort of optimal. So this is not terrible, but this is not amazing. Okay. So can you do better? By the way, this was done with fairly large buffers. You can configure network much more aggressively if you have trimming. So if you have trimming, you can say, well, I'm going to set my my trim threshold at exactly 1 BDP for every single port. And if you do this and you still use oblivious, you get this, right? So you go from like 250 to 220. And the intuition here is kind of cute. So basically, you're doing random placement, and on some of these paths you have growing queues. Now, because you have growing queues, when you hit the trim threshold, you get a trim, it goes to destination, the NAC comes back, and you pick probabilistically a new path. Now, with high probability, you will not pick this bad path because the bad paths are an outlier typically, and you'll pick a good path. So you get this indirect load balancing that happens because of trimming, right? And actually, you can, what this graph shows is really that this works. Choosing enough entropies works in all cases. So let me sort of walk you through these graphs. So these are simulations of different network sizes and different loads in the permutation traffic pattern, and all of them are the same size, so 2 megabyte flows. And what you expect is that as you have more load, then you get more collisions, right? So the z-axis shows you the increase over optimal, right? And this shows you when you do oblivious load balancing, but you just use 16 values for your EDP source port, then you basically get something like 40% increase when the load is highest, almost regardless of the size of the network. Okay. Now, if you use more values, like 64 values for ECMP, you're down to like 20%. You're down to 20% over optimal. And there is some interesting effect here that for small topologies, this actually looks worse, but for large topologies, it gets better. And the same here, if you use sort of as many values for your entropies as paths in the network, then you basically get to less than 20%, which is pretty good. But again, this is just sort of randomly choose some values, fire and forget type of thing. It works pretty well. Okay, now this works great unless you have failures or unless you have some imbalances that are just there to stay. So if you have, for instance, a path failure, what will happen with the previous approach is that you'll be sending packets obliviously and a fixed fraction of them will go over the failed link and just be black hole for some time. Of course, the routing protocol will react maybe in like 1 or 2 seconds or faster, slower, depending on what it does. And then after 2 seconds, then the path will be removed from circulation, and then you won't see this problem. But in those two seconds, basically all of the connections will be affected, and they'll be sending packets over that bad path just continuously, right? Now you can do a lot better than this, right? So the idea here is to basically keep a small amount of state per each EV, right? So let's say I have 64 EVs or 128 EVs. If I keep just 3 bits per EV, or even like just 1 bit per EV to know whether it's good or bad, right? if I get a timeout on a packet, I can see the EV it was on. I can basically mark that EV as being potentially bad and not use it, right? Even that is a big win, and it will avoid having a lot of flows being affected for a long time when you have a failure, right? But you can do even better. You can basically use congestion information to decide how much to use these EVs rather than just blindly spread traffic across them. And there's really two proposed solutions in the EET. By the way, this part is just sort of informational. Nobody says this is what you should do. This is a sender specific algorithm. Senders can do whatever they want with the congestion information they have. So this is a place where vendors can differentiate. But there's two options there. One of them is this thing called bitmap, where if you get an ACK with an ECN mark, then you will set a penalty value for that particular EV, and you skip it once when you're meant to choose it for the next packet, and then clear that mark. So that means, if I get an ECN mark, next time that path will get one less packet in the next round. And of course, depending on how many bits you have, you can play with this stuff. But given that which you can just with 2 bits you have 4 states possible, even with just 2 bits per state, you can still do quite a lot of things. A more fancy solution is this thing called recycled entropies, where you keep a cache of good entropy values, right? So you start by using random entropy values, and then when you get an ACK back, and the ACK tells you that EV was good, you didn't get an ECN for it, then basically you just put it in your cache. And when you're meant to use it, you take it from the cache. So this is very, very nice, but it turns out it works only if you have 1 ACK per packet, and you have to implement this cache structure, so it's a bit more complex to implement. So just to give you some sort of idea of how these things fare in practice. So this was oblivious with large buffers, 250, right? Oblivious with trimming is somewhere here, right? This reps thing, but if you use coil stacks, does not do better than oblivious with trimming. But if you have ACK per packet, it actually does quite well. So it does the best of everyone. And then bitmap is sort of somewhere in the middle. Now, I don't have time. I mean, obviously, there's a lot more simulations I could go over, so I don't have time to go over that. Yeah, I think I'll just stop here. Do you guys have any questions? I have this crazy sun in my face from my window. I have to duck. Is anybody still there?
Any questions? Yeah, question.
I have a question. You mentioned there are 2 ways for vendor differentiation, right?
Yeah.
Are there any publications about any one of these 2 ways, or analysis for each one of the 2 ways?
I think there's multiple places where vendors can differentiate, to be honest. So the load balancing algorithm is one option. I mean, there's quite a few places. This stuff is quite fresh. So I don't think there's a single vendor that has a product on the market now. And I would assume UEC compliant, completely UEC compliant devices will take some time to appear. Of course, the congestion control and this SAC-based behavior trimming and everything, there probably are some solutions out there, but they're not spec compliant. So I'm not sure I answered your question, to be honest.
Okay, that's fine. Thank you.
Any other questions? Go ahead.
Hi, Boris Hasanov. Thank you. So you haven't touched questions or topic about how collective communications libraries like maps to these UET extensions, like how they impact or UET impact them. Can maybe you please point to some publications or publicly available information about that? Thank you.
Well, the summary is okay. So there's two parts to that question. So if you're talking mostly AI, let me see if I can have some backup slide. Let me just see. Okay. So the UET is trying to cover both AI and HPC, and obviously, you require different features for these things. And the most demanding one is really HPC. So that's why there's this thing called profiles. So in terms of a NIC being compatible with UET, it's going to say what type of compatibility it has, right? So the simplest profile you have is this thing called AI base, which is it allows you to do the sort of the slimmest, simplest implementation of in hardware. And what it supports just one MTU sense, okay, and it supports writes. It doesn't support reads, and it has this thing called a deferrable send, which means if you send and there is no posted buffer to receive, you don't get the same thing as in Rocky, where you get this RNR, and then you have to keep trying. It's like a busy loop of you keep sending until somehow you figure it out. Deferrable send basically tells the receiver, I want to send you something. If the receiver cannot accept it, it's going to say, oh, I cannot accept it now, you'll have to send it later, but I will tell you when. So deferrable send basically has the receiver tell the sender send now because the buffer has been posted. Okay. So if you take the deferrable send and the RMA write, these are sufficient to implement rendezvous and sort of data transfer for something like nickel. So, and that's why these are the simplest. This is the simplest thing you can do, right? Yeah. Obviously, for HPC, you need to do a lot more things. You want to do, you have to do atomics. You have to be able to do tagged sends and so forth, and different types of tagging. Exact match and wildcard. So there's a lot of variations that you can do. Any other questions?
Yeah, I do have a question. So thanks for the presentation. Very nice. So in these AI workloads, we know ahead of time the traffic pattern. We know it's a collective communication operation and all gathered. So we know, and also in the data center, the topology is known. So instead of doing something like oblivious, could we do something like pre-computing the optimal solution simply and just have deploy that routing configuration? So if you know that it's data parallelism, it's going to use certain collective communication. If it's tensor parallelism, it's going to use another collective communication. So based on that information ahead of time, you could pre-compute these optimal routing tables and ensure that you achieve the absolute minimum completion time, as opposed to try to use streaming or something that is more, that doesn't use that information that we know ahead of time.
Yeah, so in principle, yes. In practice, it's hard. So if you look at the Meta Llama 3 paper, I think they have it. There was this SICOM paper, I think last year or 2 years ago. I think it's last year, SICOM. But basically, they explain, how they got to scale sort of Ethernet using Rocky V2 and to train Llama 3. And basically, this is exactly what they did. So they basically tried to say, look, if we know the traffic pattern, you could, for instance, say, I'm going to do some sort of source routing, and I select the spine based on the destination GPU number or something, right? Well, something like that, right? To make sure that GPU 1 from rack 1 sends to GPU 1 from rack 2 via spine 1, and GPU 2 will send via spine 2, and so forth. Whatever, right? You get the idea. So they said this worked great until you get a single failure. At which point they just switch back to ECMP, and the throughput, the capacity drops to 50%. So yeah, so the problem there was really
Topology
it works great until you get topology changes, and then it all goes pear-shaped. The other thing that people have tried to do, Google has this thing called protective load balancing. The idea here is, well, I think this is again a SICOM paper. So the idea is, well, I have a single path transport, and all of a sudden my throughput is bad. So I have maybe like, if I look for a few round trip times, my congestion window is smaller than what I think it should be. Then I will basically just do an EV change like once, right? And then wait to see what happens. So we actually tested this, and what I didn't say this, but there was a lot of work, a lot of simulation work that went into defining this standard. So the problem with this is that PLB works really well if you have low load, like 10-20%. The higher the load is, it just doesn't work anymore. Like you change, but you still hit a bad path, and then it doesn't help you at all. So actually, let me just stop the sharing so that I can actually see something. Yeah, so PLB doesn't work either, right? So and the intuition for why any single path solution doesn't work is sort of a theoretical intuition. So you have to carry, you have to compute the placement of flows to paths for this sort of worst case traffic pattern. And this is a sort of a NP complete problem. It's called the multi-commodity flow. If you have one flow, one path, it's a sort of an integer problem. If you allow splitting the flow across many paths, it becomes solvable, like a polynomial problem, right? So it's really it really is much easier if you do multipath, like even theoretically. There's another hand.
Any other question? Well, we are almost at the end of the hour. We had 2 great presentations, and thanks to everyone for participating, and we'll see you next time.
Thank you so much. Great presentation, and we hope you keep contributing, disseminating your knowledge, and we hope to see the community of coming back to us.
Yeah, we have an AIDC IETF.org mailing list. If you have any questions later you think of, you can send it to the mailing list. We'll relay it to the presenters. And we will also, right now the meeting materials is already in the GitHub repository, and we will publish the video recording later.
Usually it's available 2-3 days after.
Okay.
Thank you so much for inviting me, guys. Bye.
Thank you so much, everyone.
Thank you.
Gently.